Okay, welcome back everyone. In this video we're going to be looking at an example of a capacitor circuit. So this is problem 21 from chapter 24, and this is one where we're given the capacitances of several capacitors, and we're given the potential difference between points A and B to be 25 volts, and we basically want to find several things. We want to find the equivalent capacitance of the circuit. We want to find the total charge stored in the circuit. We want to figure out the charge on the 6.5 nanofarad capacitor. That's the one at the bottom here. And we want to find the voltage across the 7.5 nanofarad capacitor. Okay, now before we get into the details of this, I think it's important to look at the big picture. And one of the best ways to do this kind of problem with capacitors or later problems where you have circuits is to kind of reduce it to just one capacitor. And then from there you can find the equivalent capacitance and the total charge from our basic equation that Q equals CV. And then what we can do is we can expand our circuit outwards using what I like to call CSVP. Basically what this means is that charge is conserved in series branches and voltage is conserved in parallel branches. And we'll see how to apply this to the circuit of problem number 21. Okay, so we're going to start by reducing this to a one capacitor circuit. And the first thing we have to do is take the 3 in the middle branch, which are in series, and combine those together. And you'll remember that when capacitors are in series, the equivalent is nothing more than the sum of the inverses itself inverse. And I've solved this sort of already in my notes, and you can go through the math to do this too. You'll find that this is about 5.3 nanofarads. So we already have our first answer. Whoops. I should say that this is the capacitance for the middle loop, or the middle portion of the circuit. Sorry about that. So we still need to do one other thing. We have two other branches, if you will. The middle branch is 5.3 and the top and bottom branches are 7.5 and 6.5. So that means that the equivalent capacitance of the entire circuit is 5.3 plus 6.5 plus 7.5, and that turns out to be 19.3 nanofarads. That is our actual equivalent capacitance. And so now what we can do is take this and use Q equals CV to find the total charge. So C equivalent times VAB, because that's all the way across the circuit, and so it's going to be 19.3 nanofarads times 25 volts, and that's going to give us 483 nanocoulombs. And we might as well just leave it in nanocoulombs. Okay. Now, the next step is expanding the circuit back out to its pieces, and this is where things get a bit trickier. The first thing we can do is we can expand each branch outwards, and so there's 3 branches. And when I say to apply CSVP, what I mean is each branch has the same voltage in parallel. So if this is point A and point B, we know we have 25 volts on each of the branches. And the analogy for this is it's kind of like the voltage is potential energy. I mean, voltage is potential energy per unit charge, right? So if you think of water flowing downstream, if it starts at the top of a mountain or a hill or whatever, it's going to have the same amount of potential energy at a certain height, and it doesn't matter what path it takes to get to the ground, it will still lose the same amount of potential energy. So this is kind of a similar idea. Okay, and the other thing we can do is go back and label each of the capacitances on these routes, if you will, and we know the middle is 5.3 because we found that earlier, and we also know that the top is 7.5 and the bottom is 6.5. And because we know the capacitance and we know the voltage, we can find the charge that flows through each branch, and it's not going to be the same. It turns out that the charge that flows through a branch is going to be the capacitance of that branch times the voltage. So we could say that Q that flows through the top is going to be 7.5 nanofarads times 25 volts, or 187.5 nanocoulombs. We could say the charge that flows to the middle is going to be 132.5, and I'm skipping the math, but it's 5.3 times 25. And then the charge that flows through the bottom is going to be 162.5, and when you add those all up, you get 482.5 nanocoulombs, which is good because we said that the entire charge flowing through a circuit is about 483, and I rounded a little bit with that 483. Okay, so if you wanted to know for part C the charge that flows through the 6.5 nanofarad capacitor, well, we know that that's going to be the charge going through the bottom, so that is 162.5. We can just round that up to 163 nanocoulombs. And then finally, we need to know the voltage across the 7.5 nanofarad. Well, looks from our diagram like we don't need to worry about it. It's simply 25 volts. Okay, now one more thing. We're not asked for it in the problem, but what if we wanted to completely solve the circuit? That is, to find out the charges and voltages for everything. So that means we need to break the middle, or expand it rather, back into our three capacitors. We're not going to worry about the top and bottom branches, but now what we have is that the charge going through the middle branch is 132.5 nanocoulombs, and we know from CSVP that this charge is going to apply to this capacitor, and to this capacitor. Another way to think about it is that if one side is positive Q, the other side becomes negative Q, and then positive and negative and positive and negative, and so forth. As long as you're in series, that's the way that's going to work. Okay, and we also remember from the diagram that our three capacitors are 18 nanofarads for the first, 30 nanofarads for the second, for the middle one, and 10 nanofarads for the last. Sorry if it's a little bit messy there. And to find the voltage, we simply use V is Q over C. And so for the first one, it's going to be 132.5 nanocoulombs over 18.0 nanofarads. And look at that, those nanos cancel out, and it's about 7.36 volts. You can check my math on that. Okay, the next one is going to be 132.5 over 30, which is about 4.42 volts. And then the last one is going to be, so let's call that V1, V2, and V3. The last one is going to be 132.5 over 10, which I've rounded to 13.3 volts. And when you add these three numbers together, can you guess what you get? That's right. You're going to get 25 volts. So those voltages will add up in series, which is exactly what we expect. Okay, so this was a short summary of how to solve capacitor problems. Remember, the two main steps is to reduce the circuit to one equivalent capacitance and then expand the circuit back out using CSVP.